Voyager 1 has crossed a boundary no human spacecraft was designed to explore nearly 50 years after launch. It is now sampling a strange region where turbulence, magnetic fields, and solar-driven waves behave unexpectedly. This is not simply empty space beyond the solar system. Voyager is traveling through the very local interstellar medium, or VLISM, a thin environment surrounding our heliosphere that scientists are only now learning to understand. In 2026, two new peer-reviewed astrophysical journal studies are examining Voyager's latest measurements. Their results reveal a puzzle. The spacecraft may be moving through a remarkably calm region after years of violent interstellar disturbances. Voyager 1 launched from Cape Canaveral on September 5, 1977. After encounters with Jupiter and Saturn, it continued outward, following a trajectory that eventually carried humanity's oldest operating scientific probe beyond the Sun's protective bubble. On August 25, 2012, Voyager crossed the heliopause at about 121.7 astronomical units. That boundary separated the solar wind from interstellar plasma, making Voyager the first human-made object to enter interstellar space. Today, Voyager is roughly 167 astronomical units from the Sun, around 25 billion kilometers away. A signal traveling at light speed needs more than 23 hours to reach Earth, turning every measurement into a distant conversation. But distance is not the strangest thing. The space Voyager entered after the heliopause did not settle into the environment many models anticipated. Instead, it behaved like a layered frontier shaped by our Sun. Before Voyager arrived, scientists expected the heliopause to separate our disturbed solar neighborhood from pristine interstellar space. The farther Voyager traveled, the more its measurements should resemble a stable background far from solar influence. Scientists now call this immediate neighborhood the very local interstellar medium, or VLISM. It is not necessarily a pristine galaxy beyond our solar system. It is a nearby region whose properties remain connected to the heliosphere. One major surprise came from plasma waves. Voyager detected a persistent electromagnetic hum in interstellar plasma, allowing scientists to estimate electron density continuously instead of waiting for dramatic solar disturbances to reach the spacecraft. Those measurements revealed density fluctuations across roughly astronomical unit scales. In other words, the interstellar plasma was not perfectly smooth. It contained turbulence and structure, showing that even supposedly empty space has a complex physical texture. Then came the shock events. Solar eruptions can launch enormous pressure disturbances outward. When these disturbances interact with the heliopause, portions of their energy can continue into interstellar space, eventually reaching Voyager beyond the heliosphere. Between 2012 and 2022, Voyager recorded several major disturbances, including shocks and pressure fronts. Each event became another clue that the Sun was still influencing the environment around Voyager, despite its enormous distance beyond the heliopause. One important event arrived in May 2020. Voyager was about 149.3 astronomical units from the Sun when its magnetometer detected a sudden increase in magnetic field strength over roughly 8 days there. The magnetic field jumped by approximately 35%, while plasma density increased. Two scientists identified the disturbance as the second pressure front, or PF2, a compression wave moving through the local interstellar environment far away. But PF2 had an unexpected aftermath. Instead of quickly fading, the magnetic field remained elevated. It continued climbing until early 2021, reaching roughly 0.56 nanotesla before gradually settling near a higher long-term level afterward. That prolonged enhancement became known as the magnetic hump. It lasted roughly from 2020 into 2022, while Voyager traveled outward through several astronomical units, creating one of the mission's most intriguing discoveries afterward. A 2024 study linked the hump with enhanced solar activity. Years earlier the idea was astonishing. Changes in solar wind near Earth could eventually travel outward, interact with the heliopause, and reshape magnetic conditions around Voyager. Then came 2026. A study led by Federico Fraternale and Nikolai Pogorelov used magnetohydrodynamic simulations driven by solar wind observations. Their models showed that solar cycle compression could reproduce important features of Voyager's magnetic hump. The simulations also suggested similar structures could appear again as solar activity changes. That means Voyager may not have witnessed a one-time anomaly, but part of a repeating process connecting the Sun with interstellar space. Yet the mystery became deeper after the hump faded. Voyager entered what researchers call the post-hump region, where magnetic fluctuations appeared dramatically smoother than they had been before the second pressure front nearby. A second 2026 Astrophysical Journal paper analyzed Voyager magnetic observations through mid-2025. Researchers found earlier fluctuations showed strongly non-Gaussian behavior, a statistical signature associated with intermittent, uneven turbulence over time. After the magnetic hump, that signature almost disappeared. The fluctuations became closer to Gaussian behavior, meaning the magnetic environment looked unusually smooth and calm compared with Voyager's earlier surroundings for now. And that creates the central mystery: did Voyager cross into a genuinely different region of interstellar space, or did the magnetic hump somehow filter and weaken disturbances, temporarily creating an unusually quiet wake behind it? Some interpretations suggested Voyager might be approaching truly undisturbed interstellar space. If so, the Sun's influence could extend far beyond the heliopause, potentially reaching distances around 155 to 165 astronomical units today. But the Fraternale and Pogorelov simulations argue for another explanation. Their results suggest post-hump calmness can emerge naturally when solar-driven disturbances weaken or dissipate, without requiring Voyager to cross into different interstellar material. That means the spacecraft could still be inside the VLISM, simply traveling through a quieter phase, and if solar cycle disturbances return, Voyager may eventually record the turbulence becoming stronger again in future years. This is why the debate matters. Voyager is giving scientists something telescopes cannot: direct measurements from inside the local interstellar environment. Every magnetic fluctuation and plasma signal becomes evidence that can challenge models built before spacecraft reached this region. Here is another astonishing part: the data actually reaches Earth. Voyager's transmitter produces only about 22 watts, yet its signal crosses roughly 25 billion kilometers before enormous deep space network antennas can detect it. By the time the signal reaches Earth, it is incredibly weak. Voyager can transmit scientific information at only around 160 bits per second. Every measurement arrives as a tiny stream from a spacecraft billions of kilometers away every day. And Voyager's power supply is shrinking. Its 3 radioisotope generators have steadily weakened since 1977. NASA has therefore been shutting down instruments carefully, sacrificing capabilities to keep the spacecraft's most valuable remaining science alive longer. The cosmic ray subsystem was switched off in February 2025. Then, on April 17, 2026, NASA shut down the low-energy charged particles instrument after nearly 5 decades of continuous operation, freeing precious electrical power. A power-saving strategy known as the Big Bang is being tested on Voyager 2 during 2026. If successful, the approach could create enough electrical headroom for Voyager 1 to preserve key instruments and extend operations. Those remaining instruments matter enormously. Voyager's plasma wave system and magnetometer continue sampling the environment responsible for these discoveries, giving scientists a rare chance to watch the VLISM change in real time today. And Voyager is now helping newer missions too. Its measurements provide crucial outside the heliosphere context for missions such as IMAP, helping scientists interpret how our heliosphere interacts with the surrounding interstellar environment today. Voyager's importance reaches beyond this single spacecraft. IMAP, launched in 2024, studies the heliosphere from near Earth using energetic neutral atoms. Voyager provides the outside perspective, measuring the plasma and magnetic environment beyond the boundary. Together, these missions let scientists compare what happens inside and outside the heliosphere, creating a clearer view of how our solar system meets the galaxy. The engineering story may be even more unbelievable. Voyager launched in 1977 with a mission expected to last only a few years, yet in 2026, it is still transmitting scientific measurements from interstellar space. Its plutonium-powered generators are fading, its instruments are being switched off. And every what now matters engineers are effectively negotiating with physics to keep humanity's interstellar laboratory alive. That is why the post-hump mystery matters so much. If Voyager has entered a new region, scientists may need to rethink how far the heliosphere influences surrounding space. But if this calmness is temporary, the next solar cycle could send another wave racing outward. Voyager might then become the first spacecraft to watch that distant environment transform all over again. And eventually, Voyager will fall silent. The exact ending is uncertain, but its scientific legacy is extraordinary. A spacecraft designed during the 1970s is still revealing structures that researchers are debating with modern simulations. Its measurements have transformed the heliopause from a theoretical boundary into a dynamic physical system, constantly responding to the Sun, the galaxy, and space between them. So remember what Voyager is doing right now. It is not simply flying away from Earth, it is moving through an invisible ocean of plasma and magnetic fields, recording disturbances created by solar activity years earlier. Every faint signal tells scientists something about the environment surrounding our entire solar system, and those signals are arriving from nearly one light day away. That may be the thrilling part. Voyager 1 is almost 50 years old, billions of kilometers away, running on a shrinking power supply, yet challenging scientific assumptions. The VLISM remains mysterious, the post-hump debate is unresolved, and the next solar-driven disturbances could change everything. Humanity is still learning what lies beyond the heliopause, one signal at a time.